Hello, everyone. For this module, I would like to talk a little bit about the misuse of data and statistics. And I was going to focus this module on the misuse of data in marketing and advertising, but I stumbled across some sources that I think are much more universal and much more applicable. So I'll talk a little bit about data and marketing in some of the examples that we use in this presentation, but really this is a more general presentation on the misuse of data and statistics. So statistical analyses, we talked already this quarter about research. And so what we're going to do is kind of carry that conversation a little bit forward because statistical analyses are kind of becoming the stalwart of both the high-tech and the advanced business industries. We're really using a lot of data and a lot of research to help drive direction on what high-tech companies should produce, what high-tech companies should do, and what business analytics should drive, what activities should business analytics drive. So statistical analyses are really granting businesses an insight into solving extreme uncertainties in the market, things that we just didn't know before. Now we can actually make decisions that are data-driven decisions. Using statistics and analyses gives us the opportunity to make sound judgments and actions that are carried out according to evidence and not just based on assumptions, because assumptions is what we really had to use in the past. We just kind of hope that our assumptions were right. Statistical studies can assist in the marketing of goods or services and then the understanding of target markets. So we're using analysis now not only to understand our current market, but to understand where is the market going, what is market demand going to be, and how can we best position our products to support or to meet that market demand. So statistics in business is there's kind of a process, and there's a way that we do this. The first thing that we do is we think about either an opportunity or a problem or a question. So we may want to know, how well do we believe a certain product is going to fit a market in the next 6, 12, or 18 months? Or what are the indicators that seem to suggest that a particular product is going to be a good fit for the market? These are all questions, and they're kind of initial business questions that we use to sort of set up a study or set up what it is we want to find out. Then the next thing we do is once we have a question, and we might also refer to these as research questions, we put together an analysis plan. And the analysis plan, the point of the analysis plan is to sort of determine who needs to be involved in this study, what data do we need, how will we set it up, what is our sample going to be, who are we going to apply the results to, all that information that we would normally want to know about a particular study. But the two things that come out of this that are really high importance are, first of all, what is the research question or questions that we're trying to answer? And secondly, we'll state a hypothesis. And the hypothesis can be in the form of, we believe that this product is a good fit for the high-tech marketplace in the next 12 to 18 months. Fine, that's a fine hypothesis, okay? Then what we'll do is we'll go ahead and we'll gather data, and we'll start analyzing that data, and we'll conduct the study. When we get the data analyzed, we do some additional sort of identifying what the meaning of the analysis is relative to our research questions and our hypothesis. So we either prove or disprove our hypothesis based on what we've learned from the data. And that should all be fine, right? That's a very sort of streamlined, straightforward process of identifying a business problem or a question and running it through that entire analysis process. The problem is statistics are infamous for their ability and potential to exist as both as misleading and as bad data. So it's not statistics in and of themselves. Statistics have been shown to been developed over the last hundreds of years to be something that is highly dependable and highly reliable. And it's something we actually use quite a bit to say, we have this particular hypothesis, we're going to test this hypothesis and determine the extent to which we can support it or reject it. And that's all very numerically based. The problem comes in the interpretation of the results. And that's what we'll talk about for the rest of this presentation. So misleading statistics, the misusage, purposeful or not, of numerical data. And really, you would probably want to say numerical results, but it could be the data as well. So results provide misleading information to the receiver, okay? And that can be intentional or accidental, but oftentimes it is intentional. We're intentionally trying to get the receiver to believe a message, okay? The receiver will then believe something is wrong if he or she does not notice the error. If they don't go back and look at our research and sort of question our research and question our study, they're going to find, they're going to start to believe what we've told them, and they have no reason to not believe it, okay? So what we're going to do next is we're going to take a look at some of the most common misuses of statistics and data. So why do they do it? Before we look at the actual methods that they use, let's talk about why do they do it. So for statistics to be useful, they have to be truthful, and they mostly are. They mostly are, but the results can be distorted, as I've indicated. There's the opportunity for presenting distorted results. Seeking profit or gain by distorting the truth is one of the most common ways or common reasons why somebody who's conducting a study would in fact misinterpret the results. So that gain can be either kind of economic, there's money to be made, educational, there's educational achievements or academic achievements to be furthered. Mass media, mass media is trying to grab the headline or put together something that is exciting to its audience. And there's also political. Politicians do this all the time, or there could be political movements that are doing this. Okay? So that's really some of the major reasons why people misuse statistics. And in fact, if you think this is a small problem, it's actually not. In 2009, there was a study, basically it was an anonymous study, where researchers could sort of pony up if they've in fact used any sort of questionable methods. And 33.7% of scientists admitted to using some questionable practices. Some of those were modifying the results of a study to improve the outcomes. Some of those were subjecting data interpretations, are subjective data interpretations, which basically means instead of purely reporting on what the data reported, I sort of kind of steered the results into a particular direction to support what I wanted it to support. Some were just withholding analytic results. Oftentimes studies will reveal multiple results, and those multiple results, some of which can be really useful and some of which can be really counter-useful. And sometimes a researcher will leave out the counter-useful ones. And then there's also just instances of researchers that just drop observations because they feel like they're not right. Even though the data returned a particular result that said, this is what the data is telling me, this is what the study is telling me, the researcher looks at it and goes, nah, that can't be right. And so they just drop it without any further testing, without actually validating that it's wrong. So here are 6 ways that statistics can be misleading. One is faulty polling. One is flawed correlations. There's data fishing. There's misleading data visualization, purposeful and selective bias, and using percentage change in combination with a small sample size. I'll talk about each one of these in a bit more detail. The first one is faulty polling. Now, often when we do, and this applies to scientific, business, technological, political surveys, where we're trying to gather information from a collection of respondents. So what we do is we put together a questionnaire, and that questionnaire hopefully will give us what we want. It will hopefully give us the answers that we want, the answers that we're looking for. And the construction of such a questionnaire or such a survey, there's a real science to it. It's really important that we do the best job we possibly can of getting the data we want without biasing the questions. But there is a common practice amongst some researchers and some businesses to actually construct survey questions. And this works in political causes as well, but to construct survey questions in such a way that they sort of steer the respondent towards the answer that they want. And the first 2 that I have posted on this slide are 2 examples. The first one is, do you believe that you should be taxed so that other citizens don't have to work? And the second one is, do you think that government should help those people who cannot find work? I would say both of these, while they're kind of focused on the same thing, they're both loaded questions. And the first one is a loaded question because it's got the issue of the taxing there, right? It's not such a matter of whether or not the government should help people who can't find work. It's got this issue of should you be taxed, inferring that in fact the only way that the government can help people to find work is if they tax you to do it. So that, of course, is going to oftentimes be answered no, not because they don't believe that the government should help people find work, but they don't want to be taxed. So that is clearly a loaded question, and it's the kind of strategy that can be used in faulty polling. The other one goes on the other side. It sort of pulls or tugs at the heart. Do you think that government should help those people who cannot find work? Well, okay, yeah, I feel bad for them. So that's also a loaded question because it's not really getting at the real issue. It's getting at, do you think the government should help people? Well, okay, the question is really about unemployment programs and unemployment assistance. So when you phrase it in that way, it's more kind of an appeal to the heart. If you look down on the slide a little bit, there are 2 alternative questions. The first one is, do you support government's assistance programs for unemployment? Okay, that's pretty unbiased. It seems pretty clean. And the other one is, what is your point of view regarding unemployment assistance? Also fairly unbiased and fairly clean. Now, they're going to yield, open-ended answers. So that's just, it can be a variety of different things. But there's no real bias in the construct of the questions themselves. And that's useful. That's more useful. And that's more probably what we'd want to see when we construct a survey or a questionnaire. There's one other practice that can be used in a survey, even if we're using one of these non-biased questions, and that is to precede the question with a conditional statement of fact. And the conditional statement of fact is intended to steer the respondent towards a particular answer. And I've given you an example there, which is given the rising costs to the middle class, do you support government assistance programs? Okay. Well, the support for government assistance programs looks very much like the unbiased questions above, but now I've thrown in, given the rising cost to the middle class. What does that really have to do with the question itself? Again, it's intended to modify or alter the real meaning of the question, hopefully to get a desired result. So that's faulty polling. The next example of misuse of statistics is flawed correlation. Now, on the data side, already we've talked about what correlation is, and we know that correlation measures the relationship between two variables. If they're highly related, then they'll probably have a high correlation or a correlation that is close to 1. And if they're highly uncorrelated, where they're very different, then they'll have a correlation close to -1. And if there's no relationship at all between the variables, the correlation will be close to 0. Okay? So we can go out and find correlations of anything, right? We can find correlations of things that would really not be related at all. And that's a common practice because when you find a correlation, then you can start making statements about what that correlation means. So flawed correlation is where we manipulate the data so that the correlations can be found, even if they're not really there, which is leaving data in or putting more data in or leaving data out. Or we can artificially apply meaning to a correlation. And here's a good example of the second one. So assume that we found a correlation between an increase in car accidents and bear attacks in the month of June. So what does that mean? Okay, well, does it mean that car accidents cause bear attacks? Probably not. Does it mean that bear attacks cause car accidents? Probably not again. And we'll come back to why those are fundamental problems with those first two. Does it mean that car accidents and bear attacks partly cause each other? Probably not. Does it mean that car accidents and bear attacks are caused by a third factor? That's a possibility because that third factor could be population increase. And the more people there are, the more car accidents, and the more people there are in an area, perhaps the more bear attacks. So that's a possibility that we can investigate. Bear attacks are caused by a third factor, which correlates to car accidents. Also, a possibility we could investigate, with the third factor being population growth. Or it could be the sixth one. The correlation is purely by chance. It just happens to be that the one variable is going up and the other variable is going up, but there's no significant or practical meaning to that correlation. So we really have to look at this. Now, going back to those first two, the first two have cause, and cause is not correlation, and correlation is not cause. Correlation means, and that's what that last part of the slide, inferring causation from correlation. Correlation means that two variables are related in the sense that when one goes up, the other goes up, or when one goes up, the other goes down in a predictable and regular fashion. Okay? It does not mean that one causes the other. I mean, that's basically the fact that those two variables are related is the end of correlation. That's all it tells us. It does not give us cause. So whenever you see something correlated, and somebody is inferring causation based on a correlation, you know that they've overextended the research. Data fishing is where we don't really follow our data analysis process. Remember, a data analysis process is we set up a study and we identify research questions, and then we formulate hypotheses, and then we construct a study that is founded on those research questions and hypotheses in order to prove or disprove the hypothesis and get to a result. Okay? With data fishing, all we're doing is basically browsing the data and trying to find interesting stuff in the data. So we can set up a study with no research questions and no hypotheses, and so we're really not clear about what we're even looking for. And then we browse the data to look for interesting things. Once we find something interesting, we can then set up a study as if the interesting things we were looking for is what we're looking for all along. And it's a little bit backwards and a little bit dishonest. It doesn't mean that the results that we found are not interesting. It just means that it's really not anything that was connected to research. It was on anything that was actually connected to kind of a long line of outside research It's not what we were initially looking for. We didn't really set it up as a study. Okay? And the results may not hold up. I've then identified there on that fifth bullet point what the proper research process is. Number one is to state research and questions. Two is to establish your hypotheses. Three is to test your hypotheses. And four is to report your results. But when we do fishing, what we're doing is we're jumping ahead to item number four. The researcher is presenting what he or she has found that is statistically significant and interesting, but it may not have any practical significance and it may not be tied to any other studies. Misleading data visualization. So data charts and graphs are used to support a study's findings. They're really intended to be visuals that further the understanding of what the study has found. That's all their role is. Okay? And these charts should have information on things like the scales that were used. When we're showing numbers, what do the numbers actually mean? The starting value, very often that's 0, or it could be some other value, so that we can see the scale and the information as it relates back to the starting point or the 0 point. And it should have some information about the method of calculation. How did we calculate the results that we're seeing in the visualization chart? Absent any of those, then we probably need to question the visual, because what is the visual actually trying to show us? So there's a number of common data visualization mistakes. One of these is failed calculations. I've seen pie charts where the pie chart should add up to 100%. You're basically what percentage of 100% or what percentage of the whole is each of the pie pieces representing. But then we see the numbers adding up to 203%. So clearly that's a flawed chart. The calculations are not correct, they're failed. We're choosing the wrong visualization. We're using, like, for example, a pie chart when we really should be using a scatter plot. So the visualization that we've chosen doesn't really tell us anything, or doesn't really tell us much, or it tells us false information. We throw too much data into one visualization. There could be too many dimensions, or too many bars, or there could be too many different categories. And so not only is the visualization not useful, but the visualization can be misleading in the sense that we can't really make heads or tails out of it. We could be coming up with a data visualization that is, trying to be original and trying to be unique. But in our efforts to be original and unique, we're kind of missing the point. We're not really reporting the data as we should be reporting the data. Or we create a chart where we don't really explain fully what the chart means, and we don't give the user enough, or the reader enough information to make sense of it. And so the reader has to do too much work, or the chart that we've given them isn't really tied back to the text that is part of the study. Okay, number 5 is purposeful and selective bias. So this really has to do with how we set up the study and what we allow to be in the study. And there's two ways. It's really what we're talking about here is bias. And there are two types of bias. The first type is purposeful bias. It's where the researcher has made a selection about what he or she is choosing to report out of the results of the study. Okay, so we pick one thing that we want to study, and then we study it, and we come up with multiple results. And then from those multiple results, some of those support our hypothesis and some of those don't. And so what we choose to do is accept the ones that support our hypothesis and throw out the ones that don't. And that is purposeful bias. So the sampling method was probably used, but a researcher decides to leave part of the results out and get a significant result. We're basically separating out the final results so we can get something that we really want. Selective bias is a little different in the sense that we introduce our bias when we select our sample. So remember, when we're doing a study, oftentimes what we'll do is we'll select a sample of individuals who represent in all significant ways the demographics, age, culture, whatever, of our population, so that when we actually find results with the sample, assuming the sample size is large enough, we will be able to generalize that back to the population. We'll be able to sort of apply what we found to the population. A selective bias would be when we might want to actually learn something about all adults age 18 to 65. So we're going to run a study and we're going to select a sample, but we're really interested in more of what's going on in the younger group, the younger crowd. And so we select a sample of adults from 18 to 35. Okay? Then we run our study and we get our results. Then when we try to generalize the results back to the population, we can't really, because the population is 18 to 65 and our sample is 18 to 35. So our population, or our sample, is not representative of our population. But the researcher goes ahead and does it anyway and says, this is what we found. And he may have actually selected younger people because he has, because that was more likely to give him the result he was looking for. So, and where the flaw comes is in the selection of the sample and the application of what he found in the sample back to the population, because the sample doesn't represent the population. And the last one is using percentage change with a small sample size. First of all, a small sample size is a common problem with studies, right? An insufficient sample size. Remember, the sample size should be big enough to give statistically significant and generalizable results about the population. Not only does it have to be large enough, but it has to actually represent all of the different factors of the population. Okay? But sometimes when a researcher has used a small sample size, and this oftentimes happens in qualitative studies, but it can also happen in quantitative studies, the actual change that one observes is really, in as far as hard and fast numbers goes, really doesn't look very interesting at all. It may have gone from 35 people to 36 people, or it could be something where you're looking at the response of 21 and suddenly you have a response of 23. So an increase of 2 just doesn't look like it's all that interesting. But when you capture that as a percentage, that increase of 2 is much closer to 10%. So even though it's a small sample, the increase of 2 represents a 10% increase, which is actually a much more important or important looking result. But it's artificial, it's fake, and it's basically a larger part of a smaller thing. And in reality, it probably have no significant or practical significance. It doesn't mean anything in the real world. Here's an example of the percentage thing. So in the first panel, we have, you should check us out. We're the fastest growing religion in the country. And the second guy says fastest growing is a dubious claim. First guy says it's true. We grew by 85% over the last year. And then the other guy says, hey, Rob, want to join my religion? He says, sure, whatever. So it looks like my religion grew by 100% this year. Since we have 38,000 members, so hope they're all okay with being in second place. So that's just a kind of a real extreme example of how, an N of 1, add 1 to it, becomes a 100% increase. And that's kind of how researchers can make their research way more interesting, way more significant by using percentages. Okay, let's talk about misleading statistics in real life. And I've got 3 examples for you. The first one was presented to Congress, the United States Congress, in 2015 when they were having a conversation about defunding Planned Parenthood. And this is the chart that was presented. And it shows that from 2006 to 2013, there was a substantial reduction in cancer screenings and prevention services, but there was a substantial increase in abortions. And the Right to Life faction was using this chart to say, why are we giving $500 million to Planned Parenthood when they go against what we believe in? Well, one of the first things you can notice about this particular chart is that there is no vertical axis. So we don't know what these arrows really mean relative to each other. One of them could be a reduction of a very small percentage, and the other could be an increase of a very small percentage, or the other could be a reduction of a very large percentage. We just don't know because there's nothing over there on the left-hand side to show us what that x-axis means. It just shows numbers of increases. So if we were to actually apply some better visualization practices to this, we could look at this with a x-axis that runs from 0 to 2.5 million. And we can see then the abortion procedures and the cancer screening and preventive services. Okay? What this is telling us is something more significant, right? The abortion procedures for Planned Parenthood services is a much smaller part of what they do. And while the cancer screening and preventive services have declined, and they have declined, there's no doubting that, from 2 million down to what looks to be about a little less than 1 million. That is still much more of what Planned Parenthood does. But in the previous chart, what we saw, it looked like, oops, let me go back. Oh, let me go back to what I was doing. Okay, the previous chart, we didn't get that scale, right? We didn't see that the cancer screening and prevention services was so much more. Even though if you look at the numbers, on that purple line on the left-hand side, you'll see 2 million down to 935,000. But it looks like it's on the same exact scale as the abortion services, which is just under 300,000 going up to 327,000. So that's a misleading scale. In the next slide, we get to see a better example of that scale. And in the third slide, we get to see that scale relative to the 0 point. So what we've done here is we've taken the figures for 0.06 and we've said those are the baseline. And we have the baseline for abortion procedures and the baseline for cancer screening and preventive services. And we see the level of change year to year, or from measurement point to measurement point. Looks like they skipped 2008. But we see that for abortions, it's gone up slightly in 2007, got up again in 2009, but then dropped substantially relative to the 2006 baseline. Went up slightly in 2011, dropped again in 2012 relative to the 2006 baseline, and seems to have leveled out. So the real figure here, the real factor here is that these are two completely different kind of apples and oranges comparisons. Or the way that we should be looking at them is much more either relative to their baseline, relative to each other, or relative to a baseline, like we're showing here. And this original chart was actually called out by a number of not-for-profits that said, wait a minute, this is just bad representation of data. This is a bad visualization because it is intentionally set up to mislead the viewers. The next example we have is Colgate. It was called out by the British government because they basically said that 80% of dentists surveyed choose Colgate. Okay, well that means that sort of implies that they choose Colgate over every other brand, and that only 20% would choose something else. The reality is 80% chose Colgate, but they were allowed to choose as many brands as they wanted. So you basically lay out 100 different brands of toothpaste in front of these dentists, and 80% of them picked maybe 20 different brands, and one of those brands was Colgate. Okay, so 80% of the dentists chose Colgate. Yes, they did, but they did not do it exclusively. It wasn't the only one that they picked. So that's why the British government called them out. And this is just an example of using misleading statistics in advertising, how data can actually mislead in advertising. We've already talked a little bit last week about the issue of global warming and climate change, but here's some information that has been presented from those folks that kind of deny that climate change is really an issue. The first chart that they're showing, and the one chart that they actually show, or the first chart, I'm sorry, but the one that they actually point to, is from 1998 to 2012. In 1998, the average global temperature was 53.3 degrees Celsius. In 2012, the average global temperature for that year was 53.2 degrees. That was a 10%, 1/10 of a degree drop. So there really is no climate change, right? There's no global warming. The data are false. Here's proof, conclusive proof, I should say, that there is in fact no global warming. The problem is the data that they left out. Just like we were talking about last week with global climate change, a lot of what the climate change deniers are, the tool that they're using is to leave data out. In 1998, the world experienced a very strong El Nino, I think it was El Nino, which is a result of ocean temperatures being really high. So for whatever reason, natural or otherwise, ocean temperatures are really high, and the global temperature was artificially high in 98 as a result of that. So when we get to 2012, and in fact, without the El Nino, the temperature is almost exactly the same. That's actually a cause for worry, not a cause for proving that global climate change doesn't exist. In the next graphic, we can look at the global temperature across a larger span of time. So we go back to 1980 to 2012, which is 32 years. And we see that we have in a much more pronounced trend, right? We can see that the span that we were looking at earlier, 1998 to 2012, well, we can see 98 here. We've got that spike for the El Nino over to 2012. That looks kind of like what they were showing. But what they left out was this bit of information going all the way back to the 80s, where we have seen a substantial increase in the average temperature across the globe. And then if we take it back one step further, we could look at all the way back to 1900, and that's a much more telling story. In 1900, all the way up to 2012, we can see definitely a trend. If you look at the very end of that graph, you'll see that there's a lot of spikes there and it looks like it's leveling out, but the trend over the longer period is what's interesting here. So we need to learn to read statistics with a critical eye. And a couple of things that you can think about when you're doing that is if you're looking at a study, first of all, ask yourself, who did the study? Who conducted the study, right? Now, you're going to get authors who have been identified as the authors and the researchers, and they're the ones who wrote whatever article or whatever came out of the study. Who are they? Who are they affiliated with? If they're affiliated with an independent university, that's probably a good thing because there's no real pressures most of the time. No real pressures. There's less pressures, let's put it this way, for them to actually produce a result one way or another. If they're affiliated with a lab or a research team, then there might be financial pressures. There might be financial gain for certain results. If they're a consultant, again, there may be certain financial reasons for the consultant to sort of introduce bias. So but just ask yourself, who did the study? And then the next thing you can ask yourself is, well, who's paying them, right? Oftentimes there are grants at universities that pay for research, but if you're in the corporate world, then you have to think about who stands to gain from actually paying for a particular study, or who pays the researchers or provides the resources for the study. You might ask yourself, what are the motives behind the research? Go back to the original sort of design of the research. What was the research questions? What were the research questions? So what was the researcher looking to find? And did the study really find that? Or did it sort of find that and you feel like the research was kind of utilized or used to sort of help prove something that it didn't really prove? Ask yourself what the researcher was trying to figure out. Okay? One thing I would always caution you to do is to take a look at the sample size, right? How big was the sample? And was the sample truly representative of the population? Okay. Who was allowed to be in the study? And is there any sort of documentation, any sort of description of how the selection of the sample, the selection of the respondents actually truly represented the population? One last thing to think about is the best scientists and the best procedures and the best data and the best samples can all be utilized in a study, and it can produce a result that we have very high confidence in. There's low opportunity for bias. The results actually are significant. Problem is, they're not very exciting, or only part of them are exciting. So what happens in that case is that we can get into a problem of something called study amplification. And study amplification is where we take results and turn them into headlines. And we've talked about this a little bit in some of the other presentations. So nobody's going to care about a study that has boring results, or nobody's going to care about a study that appears to have boring results, even though the results might be significant on a number of scientific or business or technological fronts. So what the media does, and social media does this a lot as well, is it turns it into something that is exciting, something that's going to get you to read the article that they've written, something that's going to sort of turn your head. And those are sound bites, things that will grab your attention. But oftentimes that can be misleading on its own. Even the best research can, be reported in the popular or social media, in a way that distorts the meaning of the articles. And that's not on the researcher. That's on the person who's actually reporting it in social or popular media. So it's something you'll see very commonly. Okay, so now you know. So now you know how to differentiate good from faulty studies, how to differentiate good from faulty statistics. And part of what we've learned in this class this quarter is some statistical methods, and that was largely by design, so that when we got to this point of the course, you would have a better understanding of some of the tools that researchers can use. And as you start to understand some of the tools that researchers can use, you can get a better idea of how they might use them to produce questionable, biased, or even faulty results. Okay? But crafty researchers can still fool even experts. Okay? And they'll do that if we don't look at or question their methods. Okay? If we don't, I should say if we don't actually examine how they have interpreted their results, and if we don't question how they have applied their results, if we don't look at, kind of what they're doing in their research and really question it, then we might get ourselves into a position to sort of accept something that really isn't there. Now, the nice thing about this is that the academic and scientific community is a really good check, that does a really good check of each other. And most of the research that is produced fits a very rigorous sort of examination by academic and scientific peers who are going to look at the research and determine whether or not the research methods used to achieve the results are in fact trustworthy, free from bias, and are constructed in such a way that the results can follow from the process. That's great. That's great in the scientific and academic communities. But does that always happen in the business community? Does it happen with marketers and advertisers? Does it happen with politicians? Does it happen with a whole trove of other people who use data and statistics in order to manipulate or impact the public opinion? And so I think it's important for us to be armed with these skills, armed with these methods of questioning what is coming out of a study or how somebody is using data, in order that we aren't fooled and we can actually apply a critical eye.